Okay, we're live.
Okay. Hello, everybody. Welcome to the Latin American Webinar of Physics. I'm Camilo García-Cely from DESY in Hamburg, and I'll be your host today. This time, we have a very interesting colloquium by Andreas Ringwald, who will tell us about the quest for the axion. He's one of the authors of the review of axions for the particle data group, and it's one of the leaders of the ALPS collaboration, whose main goal is the search for axion-like particles. Andreas Ringwald obtained his PhD at the University of Heidelberg in Germany. And after some research positions at DESY and at CERN, he became staff scientist here at DESY. And okay, so before we start the talk, I would like to encourage you to ask questions. You can do that by typing them in the designated box in YouTube, which you can find on the right-hand side of your screen. At the end of the colloquium, I'll read the questions for everyone. And okay, so thanks, Andreas. Please go ahead with your presentations.
No, thank you very much for the invitation. So I'm doing this with pleasure. So I'm talking about the quest for the axion, and we start right away. So so we all are appreciating the success, the overall success of the standard model, which describes the interactions of all the known particles with a remarkable accuracy, which I have here, for example, is here summarized by the comparison of the standard model total production cross-section measurements of the Atlas collaboration at LHC, in comparison of their measurements with the theory in gray, and you see, I mean, where there are really very good data. So the data are exactly on the theoretical predictions, and so it's and there are many other examples. There are few places where the standard model might be endangered, but they are typically maybe two or three sigma things. For example, in B physics, there is at the moment, or in flavor physics, there are some hints of things, but overall, the standard model at the moment describes the interaction of all the known particles with remarkable accuracy. But as soon as we go out and look into astrophysics or in cosmology, then the standard model doesn't seem to fit. So there are observations in particle physics, astrophysics, and cosmology which strongly suggest physics beyond the standard model. So there is one are the neutrino masses and mixing, which are not contained directly in the standard model. There is the dark matter in the universe, which makes from the total amount of matter in the universe, more than 85 or around 85% are not of the stuff from the standard model. There is the baryon asymmetry of the universe, which cannot be explained from first principles within the standard model. There is the question how we should describe inflation, the very exponential expansion of the universe at early stage before the so-called hot Big Bang started. There is grand unification, which is there's only a hint from the evolution of the couplings, but the hint, so within the standard model, these couplings do not meet, but maybe there is some physics beyond the standard model such that these couplings meet and give grand unification. And there are naturalness problems, so like the hierarchy problem. So the question why the Higgs mass or the electroweak scale is so much smaller than the Planck scale, or there is the strong CP problem, which are natural problems, which are not an observation in particle physics, which strongly suggests physics beyond the standard model, but maybe with one could understand these problems or puzzles better if one has introduces physics beyond the standard model. And I will, of course, we are doing axion physics, so I'm concentrating on axions. So I concentrate here now at the beginning, I concentrate on the strong CP problem, and we will later see maybe one can also solve other problems with the solution of the strong CP problem. So to go into the strong CP problem, we have to understand the notion of the theta term in QCD. Now, already very early after the invention or the discovery of quantum chromodynamics, or the proposal of the formulation of quantum chromodynamics, it was found that the most general gauge invariant Lagrangian of QCD on the renormalizable level does not contain only the gauge kinetic terms and gauge invariant or gauge covariant terms of the kinetic terms of the quarks, but there is also a third term which looks very, so from the gauge field content it looks very much like the gauge kinetic term. There's this little tilde, which means that it's a gluonic field strength, but contracted with a 4-dimensional epsilon tensor. This is the so-called dual field strength, and now so it was due to these gentlemen here, like Belavin et al., Geratov, Kellen, Gross, and Chakif and Revy. Due to these people, they found that this term on the non-perturbative level cannot be neglected in QCD. So why this term at the beginning wasn't considered? It's just because you can write this term, this chi dual term, you can write as a total derivative of a current, the so-called Chern-Simons current. And so normally you would say, so if the fields rapidly decay at infinity, you cannot neglect such term because it will be a surface term in the action, and so you don't need to consider it if you derive, for example, the Feynman rules and the rules for perturbative QCD. However, it was noted by this gentleman that this term cannot be neglected because in a non-abelian gauge theory you cannot neglect, so to say, even if the fields rapidly decay at infinity, you cannot neglect that, because there will be a contribution to the space-time integral of this quantity. The space-time integral of this quantity alpha s over 8 pi of chi dual will give an integer number, which is the so-called differences in Chern-Simons number or the Pontryagin index. So it will give a topological invariant. So you cannot. So in general, there are these fields cannot or such fields cannot be completely neglected, and the strength of this term then is now measured by a new parameter, the theta angle. It's an angle because as I said, so this gives rise to an integer. So this will be the space-time integral. So in fact, this quantity will have this kind of introduce this kind of periodicity, and therefore this theta can only range from -pi to pi, say. So this means now that the parameters of QCD are not only the strong coupling alpha s, the quark masses here in this M, but there is a third another parameter, this so-called theta angle. Now, what can be the observable features of this theta angle? There is the topological. So this term, this topological theta term, chi dual, if you write it in field strengths, it's something like the chromoelectric field strengths dotted into the chromomagnetic field strengths. And now you can easily convince yourself that this E dot B violates the parity transformation, transformation symmetry and the time reversal symmetry, and thus it violates CP because of the CPT theorem. And the most sensitive probe of P and T violation in flavor conserving interactions, because this should be now a flavor conserving interaction, unlike CP violation from weak interactions. So this is flavor. Is CP violation in flavor changing interactions. So this will be the electric dipole moment of the neutron, because the electric dipole moment of the neutron will violate P and T, and thus CP. Now, so in order to estimate, so this now to calculate the prediction of QCD for the electric dipole moment of the neutron, you need now, of course, something like you need some non-perturbative methods. So this has been calculated in chiral effective theory, and it has also been calculated by using QCD sum rules. However, you can also very easily get a rule of thumb or some estimate how big this should be. So it should be proportional. Of course, it should be a dipole moment. So it should have the units of E times centimeter. So it should be proportional to 1 over a hadronic scale. Now, first you would expect it goes like 1 over the mass of the neutron times theta times E. However, we know, so because of the chiral anomaly in the theory, or chiral Ward identities, we know that the effect should be 0 if one of the quark masses have 0 mass, and therefore so this process should go proportional to the reduced quark mass, so to say. So if you assume now that you have just the two lightest flavors, U and D, then it should be proportional to mu times mt divided by mu plus mt. So this is the reduced quark mass. And now, in order to do the dimensions right, it should have a 1 over mn squared. So the naive expectation would be 10 to the minus 15 theta e centimeter, but because of this factor, you get 1 or 2 orders of magnitude suppression in addition. So the expectation would be 6 times 10 to the minus 17 theta e centimeter for this dipole moment of the neutron. However, the experiment gives 2.9 times an upper bound of 2.9 times 10 to the minus 26 e centimeter. So you infer from that the absolute value of theta should be less than 10 to the minus 9. And so this is the strong CP problem. So you would like to understand why this theta has such a small value. Now, it's an observation that on which the axionic solution of the strong CP problem is based. It was an observation by Peche and Quinn, namely. So they used the fact that the vacuum energy in QCD, if you just now consider QCD as it is, so have the Lagrange of QCD, and you calculate the vacuum energy of QCD as a function of this theta, then you find that this has a localized minimum at theta equal to 0. So that it has a localized minimum at theta equal to 0. You can this has already been shown by Waffer and Witten on very general arguments. But the explicit expression for the vacuum energy of QCD as a function of theta can be inferred from the fact that the low energy theory of QCD is the chiral effective theory, and one can in principle you can calculate the vacuum energy of QCD then by calculating the vacuum energy of the chiral of the vacuum energy of the chiral effective theory. And here I have given the expression which people like Di Vecchia and Veneziano found, and there's a nice paper by Leutwiler and Smilga where this is all derived. So you see, so you have a potential which is periodic, in theta, and it has a localized minimum at 0, and so to say, and therefore. Therefore, if theta were a dynamical field, then its vacuum expectation value would be 0, just because of this fact. So you have somehow to find a theory which gives that low energy a dynamical field which looks exactly like giving rise to a dynamical theta term. Here, just as a final explanation, here the sigma is nothing else than the quark condensate, and mu and md are the quark masses. So, but this you can infer, can get directly, as the people Di Vecchia and Veneziano have shown. You can directly get from chiral effective field theory. Now, so what is now then the simple idea of Peche and Quinn was now taken in simple words. If you read the paper, it's much more complicated, but because it does it in a special realization. But here now from a modern perspective, you would say just you add to the standard model an angular field, so a scalar field theta a of x. Which looks like a of x, like a dimension, mass dimension 1 field a of x, a normal scalar field, divided by fa, which fa is a dimensionful constant, has units of dimension of mass. And if this field respects a shift symmetry, that if theta a of x goes to theta a of x plus constant, broken only by a coupling to the topological density to this Chi-Chi dual, like a space-time dependent theta term, then if you have such a field, then of course you can eliminate the theta, the constant theta term of QCD just by a shift. And because you have said, I mean, it should have a shift symmetry, then so you have eliminated this term. And then, of course, the effective potential of this field, of this shifted field, will be exactly equal to the vacuum energy of QCD as a function of theta, and this will predict then the vanishing wave. So P and T and CP are conserved in the vacuum, in the QCD vacuum. Now, and of course, you will have a particle excitation around the 0. You can directly read off from that the mass just by the second derivative of this potential now with respect to theta, and so the mass will be given by this combination, and you can relate the vacuum, the condensate, the quark condensates, you can relate to the pion mass and to the pion decay constant like that. And so you see, you will get, so if you insert numbers for the pion mass, the pion decay constant, and for the quark masses, you will get something like 6 millielectron volt if this constant Fa, which is called the axion decay constant, like F pi is the pion decay constant, if this is of the order 10 to the 9 GeV. And the strength of the interactions with the standard model of this particle will be controlled by this decay constant Fa. Now you can embed, so now we have just introduced this field, so we call this angular field theta, which takes value between minus pi and plus pi. Now how we can get this from a UV completion is very simple. So these are so-called Peche-Quinn extension of the standard model. So you start from a singlet complex scalar field sigma, which features a global U1 Peche-Quinn symmetry to the standard model, and you assume that it has this kind of Mexican head potential, such that this U1 Peccei-Quinn symmetry is broken by the WEF of this sigma field. Now, of course, if you now expand this sigma field around this WEF, then you will get excitations in the direction, so to say, in the radial direction, which will have large masses proportional to the vacuum expectation value of this field, but you will also have, so in the angular or in the angular direction, so the excitation of the phase, so to say, in this angular direction will have a zero mass. So it will be a massless Goldstone boson just from this breaking of this symmetry. Now this is still not the axion, because the axion should behave like a theta term. So it should have the coupling to the Chi-Chi dual. So this combination A of x over VPQ should now have this interaction. How you get that is if the standard model or extra colored fermions in the standard model or extra colored fermions carry Peccei-Quinn charges, so charges under this U1, such that this U1 Peccei-Quinn is broken due to the gluonic triangle anomaly. So if you calculate the divergence of this U1 Peccei-Quinn current, then it should not be zero, but it should be violated due to this triangle anomaly, where you have again this alpha s over 8 pi Chi-Chi dual, which is exactly the topological charge density, and there's a number n which essentially counts the number of quarks or colored fermions in this loop. So if this is the case, if the fermion content of the theory is such, and the Peccei-Quinn charge assignment is such that you have this anomalous violation of this Peccei-Quinn current, then the low energy effective field theory at energies above lambda QCD, but below the electroweak scale, which is assumed now always to be much smaller than the Peccei-Quinn symmetry scale, breaking scale. So in this case, this A of x over VPQ, this or this there is a theta. So then the field theta A of x divided by FA, where FA is now given not just by VPQ, but VPQ divided by this n, this factor from the gluonic triangle anomaly. Then this theta field will be, so to say, the angular axion field, and act exactly as a space-time dependent theta parameter and solve the strong CP problem. And so you see, this is how you embed the axion solution to the strong CP problem into a UV completion, which is renormalizable. Now, just to end this, the low energy couplings, the axion couplings to the standard model at energies below the QCD scale can finally be obtained again by using the chiral effective theory. So as I already said, the axion mass. So if you now integrate, so to say, this Chi-Chi dual term, you integrate out the gluons by matching the theory to a chiral effective theory, then you can read off the axion mass, and also the higher, the a to the fourth terms and so on. All these terms are directly given by this expression for the vacuum energy of QCD, but the mass term will be the most essential first of all, and this mass in principle can be calculated beyond the leading order chiral perturbation theory So this has been done recently by Grilli di Cortona et al. And Villadoro, and also by in next to leading order chiral perturbation theory, or by Borsani et al. By lattice with similar errors. So the axion mass, if you know the axion decay constant, is now is determined by up to an error of 1% or 10%. So which is really impressive. But of course, this is the unknown parameter in the game, this FA. And all the couplings to the standard model particles, for example, to the photons, or to electrons or nuclei, are suppressed by this axion decay constant. So if this is very large, then the axion is invisible. It's not really invisible, because we will see that it can be dark matter, and it will always decay into 2 photons. It's not completely invisible, but it has very weak interactions with the standard model. And for example, the photon coupling is then related to there is one piece in the photon coupling which arises from mixing of the axion with the pion, which is determined again by the chiral effective field theory. And there's one piece, E over N, where E is the electromagnetic anomaly contribution, and N was the color anomaly contribution. This is the model dependent factor. And also in the nuclear couplings, there is a model independent factor, and there are factors which depend essentially on the Pänchik-Wien charges of the original of the UV completion. And the electron coupling is very model dependent. So if this extra fermions have no electric charge, then on the tree level there will be no electric coupling and so on. So this was now in a nutshell the axion solution of the strong CP problem, and the predictions from QCD for the low energy properties of the axion, which are very much fixed. So there's no uncertainty in the mass, and in the others there are model dependent factors and model independent factors. Now we turn to axion dark matter. So because the interesting thing about the axion is it does not only solve the strong CP problem, but it also is a very well motivated dark matter candidate. In fact, in certain scenarios, it is inevitably produced, and so so dark matter can even give a very strong constraints on the existence of the axion. Now, so now we are assuming that the axion, that this decay constant or the VPQ scale, that is very large, and therefore the axion is very weakly interacting, and so can be a very long-lived particle. So which would mean it can be dark matter. And now we assume now we assume that in the early universe, when the temperature falls below the Pänchik-Wien symmetry scale, below the critical temperature of the Pänchik-Wien symmetry transition, where the Pänchik-Wien symmetry goes from an unbroken phase into a broken phase, then there the axion comes into the axion starts to come into the play, and therefore and shortly after this Pänchik-Wien phase transition, the axion will take random initial values in causally connected domains in the universe. So in each causally connected domain, it will have a random initial values. Now later, then when it will be frozen at these random initial values because if the Hubble expansion if the Hubble expansion is very rapid, so in the early universe, so the Hubble drag term in the evolution equation of a scalar field will fix the value of the scalar field at the initial value. And so here we show the generic evolution, time evolution, or 1/temperature evolution of the axion field or of the theta field, and you see, as long as the Hubble expansion rate is much larger than the mass of the axion, and this is illustrated here. So the Hubble expansion rate drops if you go to later energies, and the axion mass, as we will show, the axion mass turns on, because the axion mass will be proportional to the will behave as I will show a bit later, will be proportional to the square root of the topological susceptibility in QCD, and it will slowly turn on around at low temperatures around the QCD phase transition, and at some point the Hubble expansion rate and the axion mass will be of the same order, and then the axion field will start to feel the drag, the drag towards the CP conserving minimum, and will start to oscillate around this minimum. So, and then you have these oscillations around zero field. So and if you look so to say the equation of state for that, so you calculate the pressure of the axion field divided by the energy density of the axion field, this will behave exactly like cold dark matter. So it will be PA or rho A will be very small, and this means that this oscillating scalar field will behave like a coherent state of many axion of many non-relativistic axions, and so you will create an inevitably axion dark matter via this mechanism. So very recently, so there have been computational progress in order to for example to predict within the standard model the Hubble expansion, the Hubble expansion rate as a function of temperature, and also the axion mass as a function of temperature. So and for that one needs input from the lattice or from non-perturbative calculations. For example, the Hubble expansion rate is determined if you know the equation of state. If you know the equation of state, and so in particular the number of relativistic degrees of freedom of the entropy degrees of freedom, and of the heat capacity degrees of freedom. And so this has been determined to a very good accuracy now around the relevant temperatures, around 100 MeV to 1 GeV or so, which is the relevant scale for looking into the axion dark matter. And the topological susceptibility, because the temperature-dependent axion mass is given by the square root of the topological susceptibility in QCD divided FA. So this is nothing else, so to say, than the two-point function of the topological charge density. So this Chi-Chi dual correlators. And this has also been determined to a very high accuracy recently on the lattice in this paper above. And before we had, for this, we had only dilute instanton gas estimates. So now, if you take all this together, then you have to decide. Then you have to discriminate two very important scenarios for axion dark matter. There's one is the pre-inflationary Peccei-Quinn symmetry breaking scenario. If the Peccei-Quinn symmetry is broken before or during inflation and not restored afterwards, then of course the axion cold dark matter density depends on the single initial value in the domain, which becomes later our observable universe, and FA. So we have the prediction of the relative of the relative energy density in axion dark matter coming from this vacuum realignment mechanism to the critical density in the universe is given by this relation. It depends on FA power like to 1.165. This is essentially given. This index essentially comes from the slope of this temperature dependence, and it's proportional to theta I squared. So at least this is valid as long as FA is larger than 10 to the 11 GeV or so. And you see if for theta I initial value of order 1, then you need axion decay constant of the order of 10 to the 12 GeV in order to reproduce the full dark matter. Here's the general result for the pre-inflationary scenario. Of course, so you can say there is not really a prediction. So there, in this case, so you can always so if you are on this line, then 100% of the dark matter is made by axions. So so if you prefer now an axion decay constant of the order of the gut scale, then you read off from this curve, you would need an initial alignment angle of the order of few times 10 to the -3 in order to explain the universe. Everything above here would be overdense, and everything below would be subdominant. So axions would be subdominant dark matter in this pre-inflationary scenario. Importantly, in this pre-inflationary scenario, which is less predictive or is not so predictive, as you said, importantly, in this case, you will get an upper bound on the scale of inflation from isocurvature fluctuations, which are produced by the axion during inflation and not erased afterwards. So, but there in this case, you have an entropic axion window, which is where essentially you can always where the axion can be 100% of dark matter without contradicting isocurvature fluctuations and so on. Now we come to the post-inflation Peccei-Quinn symmetry breaking scenario. So in this case, if the Peccei-Quinn symmetry is restored after reheating, after inflation, then we have to average over the random initial axion field values, because now the present universe consists of many patches, so to say, which have different initial conditions at Peccei-Quinn symmetry breaking, so to say. And so so if you do this averaging, you find this result from using the latest results on the Hubble on the equation of state and of the topological sustainability. So you find this result for the contribution from the vacuum realignment mechanism. So there is, of course, now a first consequence of that is, so if you now would say, so this should not be larger, this contribution should not be larger than the observed dark matter abundance, which is 0.12, then you find from that an upper limit on Fa, or correspondingly a lower limit on the mass of the axion, which should be larger than 28 micro, or say 30 microelectron volt. So so this is the first consequence of that. So in the post-inflation scenario, you have a lower limit on the axion mass, or an upper limit on the decay constant. However, in this case, so when we did this average of random initial axion field values, we were not taking into account that there are, of course, boundaries between these domains of initially fixed values of theta I. And in these boundaries, or there can be topological defects, and so notably there can be strings, axion strings, and there can be domain walls between these domains. And in order to the collapse of a network of topological defects consisting of strings and domain walls will also lead to axions, which also therefore also contribute to the dark matter abundance of axions. And in order to get their contribution, one needs field theoretical simulations to determine their contribution to dark matter. And so this is a very active field at the moment. So here I'm reporting now of results based on the simulation of a Japanese group. If you take their field theoretical lattice simulations and take the update to the latest determinations of the topological susceptibility and so on, you find that the cold dark matter would be explained in the scenarios with n, this n equal to 1, which now I can also call this n. This was the factor from the anomaly, but here it turns out this is also the so-called domain wall number. This is the and so for domain wall number 1, you find that the cold dark matter is explained for axions in the mass range between 60 and 150 microelectron volt. This is still so, and this is only this is not so this error just takes, so to say, the limits which they found from which the Japanese found from their lattice simulations, but they could do the lattice simulation only at unrealistic values of the string tension. And recently, Claire and Guy Moore from Darmstadt, they have found or developed a new simulation technique which was designed to work directly at high string tension, and they gave a very narrow result for the axion mass in this n equal to 1 post-inflationary Paget-Wien symmetry breaking scenario of 26.2 plus minus 3.4 microelectron volt. There are still at the moment there's some tension with this between these results. However, there are further simulations ongoing as we speak by other groups which try to clarify this issue and to see where it is. I mean, if you take this at face value, then you would say, okay, the strings and the domain walls, they don't do any contribution to the dark matter, and everything comes from the virtual realignment mechanism. Whereas in this case, you would say, I mean, there is at least half of the dark matter arises from the collapse of these string wall networks. So there's so this still has to be clarified. For n larger than 1, so if this domain wall number is larger than 1, then there is a domain wall problem, because then there are topological obstructions that these topological defects can decay. However, nobody assumes, so I mean, the Patrick wind symmetry is completely exact, because everybody. So we expect that the Patrick wind symmetry will be explicitly broken at the end, for example, by Planck suppressed operators, and if you somehow find a way that the Planck suppressed operators they start only at dimension 9 or 10, then so to say, then there is enough symmetry breaking that the topological defects decay reasonably fast to produce to not to be excluded or not to be excluded cosmologically, but but still the effects are not so so that these symmetry breaking effects, they don't spoil the solution of the strong CP problem by spoiling so by moving the minimum of the potential away from zero, so to say. And if you take this, then you find something that axion that an axion mass between 0.6 millielectron volt and or a 100 millielectron volt can be explain the whole dark matter. In order to, you can realize this, that the lower dimensions are forbidden if you postulate a discrete symmetry. By the way, so a DFSZ axion, which has domain wall number equal to 6 in this mass range, would explain excessive stellar energy losses, which I will show in very soon. Now, so here is so to say so I wanted to so that the dark matter axion mass can span really a very huge range. So in the case that the axion in the pre-inflationary scenario, the axion mass can be between say 10 to the minus 12 electron volt up to a milli electron volt. And in a huge range, you need, of course, some tuning in theta I in order that it can be 100% of dark matter. There is one region where it can be dominant or subdominant dark matter, and then you can again with the tuning you can explain the dark matter in the universe. There is one region which is so to say in this case preferred. And there's the post-inflationary scenario. Now, if the domain wall number is equal to 1, you have a quite small region which is allowed, and where axion can be 100% of dark matter. And and if you have domain wall number larger than 1, for example, here 6 for the DFSZ axion model, you would be even at higher masses. Now, very importantly, in the recent years, there have been a proposal of axion dark matter experiment, which go over all these mass ranges. So for the lowest masses, for GATT scale axions, there is this Casper proposal, which want to use nuclear magnetic resonance techniques to measure directly the oscillating dipole moments oscillating due to the dark matter. So you have essentially an oscillating theta term, which leads to oscillating dipole moments. And this experiment wants to directly measure these dipole moments. There is Abracadabra, which is a superconducting current ring experiment. Then in the region where you have the least fine tuning for the pre-inflationary scenario, there is the ADMX experiment and the haystack experiments, which use microwave cavities. And these experiments, they are they are active, they are working and producing data as we speak and searching for the axion. And there are other proposals like Kaltask in South Korea, who want also to build new cavities in this range. Then in the range which is now most motivated in a post-inflationary scenario, there are new experiments proposed like MADMAX and Orpheus and Quarks. MADMAX is a magnetic dish experiment based on an idea we developed first with some others here in Hamburg, and which was then boosted by Xavi Redondo and others then later in Munich to a dielectric resonator experiment. You had a Latin American seminar about that by Xavi himself, and there is the brass experiment, which here in Hamburg is been built using just a huge, or proposing then a huge dish experiment without these cavities. Interestingly enough, also the MADMAX collaboration has now decided to take DESY in Hamburg as a site to build the experiment. So I'm really looking forward to this. Now, as I promised, there are some astrophysical hints for Axion and ALPS. Namely, there are some excessive stellar energy losses. So first of all, I should start this by emphasizing then that the evolution of stars, starting from a main sequence over the red giant branch to a helium-beryllium star, and then to the white dwarf, is very sensitive to non-standard model energy losses. So energy losses beyond the loss by emission of neutrinos, for example, and so this has always been used to put limits on axions or on axion-like particles, that the evolution of stars would be changed if there would be too much energy loss. But nowadays, it seems that practically every stellar system seems to be cooling faster than predicted by models. So this is for helium-burning stars, for red giants, for white dwarfs, and so on, for neutron stars. So they are all cooling faster than predicted by models, and it's a non-trivial fact that these excessive energy losses of helium-burning stars, red giants, and white dwarfs, if you take them all together, can be explained at one stroke by the production of an axion or axion-like particles with couplings to photons and electrons. So here is the coupling of the photon. So what I say, it's given by Ca gamma alpha 2 by Fa. So by coupling of photons, or the coupling to electrons, so electron Bremsstrahlung of axions can lead to excessive or extra stellar energy losses. And if you take all the data together, which we saw here, then we can fit everything together by an axion-like particle. So the best fit would be an axion or axion-like particle with a mass less than a kilo electron volt or so, the temperature inside of these stars, so it should have an electron coupling of the order of 10 to the minus 13, and a photon coupling of the order of 10 to the minus 11 GeV to the minus 1. And you see, so at least in this direction, so this is more than, it's nearly 3 sigma. So the best fit is nearly 3 sigma away from 0, at least for the electron coupling. So it's quite remarkable that this works. And here I have also plotted in two lines. These are the sensitivity curves for the projected sensitivities in the photon coupling of ALPS 2, which is a light shining through a wall experiment, and of YAXO, which is a helioscope. Of course, we have to assume here in both cases, so the mass should be much less than keV, and for ALPS 2 is not sensitive at keV, not even, it's only sensitive at energies below 10 to the minus 4 electron volt. So we have to keep this in mind. So what is ALPS 2? ALPS 2 is a light shining through wall experiment, as I said, and it's as we speak, it's being constructed or built in Hera North, in one of the straight sections of the previous Hera Collider, and YAXO is a helioscope, so it's a magnet pointed towards the sun, and it's the successor of the CERN Axion solar telescope. And also, so similar to MADMAX, also YAXO, the YAXO collaboration has decided that if it's built, if it's constructed, then the site will be at DESY. Now here I have just we just see so that these excessive energy losses can be explained in one stroke by the production of an axion, and here it's the example of a DFSZ axion. The DFSZ axion is characterized by two quantities. So it's of course Fa, and the domain wall number is 6 in this case, as I said. And it's the tangents beta, which is because the DFSZ axion model is based on a 2 Higgs doublet model. It has two, and this is the ratio of the Higgs, which gives masses to the up-type quarks, divided by the Higgs, by the backfolding expectation of the Higgs, which gives rise to the down quark masses. And here you see, here is the best fit. The best fit for the explanation of these things is of these stellar energy losses is in a region which can be probed by YAXO, and partly so this, because this best fit, the 1 sigma region extends here along all these lines, can also be partly probed by Ariadne, where Ariadne is a 5th force experiment using again nuclear magnetic resonance techniques, and would be sensitive from the lower mass side. So finally, I will switch gears, and now so we have I told you that the axion can solve the strong CP problem. It can be dark matter. Now I want just to emphasize that the axion, even, or the saxion, now the, so to say, the radial field, the radial part of the Patrick wind field can be, if mixed with the Higgs, can be the successful or viable inflaton candidate. So you use now one field to solve them all: the strong CP, dark matter, and inflation. So this is based on so as we have shown, Guillermo Ballesteros, Carlos Tamarit, Javi Redondo, and myself, we have shown that the mixture of the saxion, so to say the radial part of the Patrick wind field, with the Higgs modulus is a viable inflaton candidate if one takes into account its possible non-minimal coupling to gravity. So which is this kind of terms, psi star, sigma star R, and which will be, in any case, even if you set it to 0 at some scale, it will be generated by radiative corrections in any case. So what you need to get viable inflation, to get this as a viable inflaton candidate, you need that this psi sigma should be of the order of 2 times 10 to the 5 times square root of lambda sigma, where lambda sigma, so this psi sigma is this non-minimal parameter, and lambda sigma is the quartic coupling of the Patrick wind field. And all this psi sigma should be larger than psi Higgs, the non-minimal coupling of the Higgs. And moreover, the Higgs portal coupling should be less than 0. In this case, you find in the Einstein frame for the potential, scalar potential in the Einstein frame as a function of the Higgs and of the rho and of the radial direction. You find it looks like that at very large field values, at field values of the order of M Planck. You find if these conditions are met, you find a ridge, so to say, or a valley along a direction very near to the saxion direction, and a ridge along the Higgs direction. So very naturally, you can realize inflation along for the field for slow roll along this one of these valley directions. The good thing about this is it's a very predictive theory because it has a very predictive reheating. So now for FA, or the Patrick-Wind symmetry breaking scale, less than 10 to the 16 GeV, the Patrick-Wind symmetry is restored after inflation already in the preheating stage. So you calculate now these oscillations of this background field after inflations, and then, so to say, the fluctuations in the direction of the inflaton and also the perpendicular to the inflatons, they are very quickly reaching the same values, and the Patrick-Wind symmetry is restored. So this means you are in a very predictive post-inflationary scenario. The dark matter axion mass will be larger than 30 microelectron volt or so. And so this is one of the predictions of this theory immediately. And then, moreover, the Higgs component of the inflaton will allow for the production of standard model gauge bosons, and it results in a quite large reheating temperature of the order of 10 to the 10 GeV, which means then also that the axions, so to say, the thermal axions produced in the early universe, they will be thermalized, and you will get after decoupling of this, you will get an axion dark radiation prediction of the order of 0.03, which can be detected by next generation of CMB experiments. Furthermore, the expansion and the thermal history of the universe is very much predicted, because I mean we can predict, so to say, the expansion theory and calculate, so this reheating takes place you go very rapidly from an inflationary phase into a radiation dominated phase, so to say, and therefore the number of e-folds from the time a co-moving scale leaves the horizon until the end of inflation is predicted. And this has a very important consequence, namely that you get a very sharp prediction of the tensor to scalar ratio versus R versus the spectral index. And so you get this tiny band is the prediction of this saxion Higgs inflation, and this prediction here is it's compared to the present bounds from CMB TT and other cosmological CMB data, and now if you now consider the projected sensitivity of the upcoming CMB experiment, for example, here CMB stage 4, you see that this sharp prediction can really be probed within the upcoming decade of CMB experiments, which I find very exciting. Now, and so this brought us to the idea to unify now even more to unify inflation, dark matter, and the seesaw with the Patrick-Wind field. So to get one smash to rule them all. So not only to introduce now the axion, and for example here, like in our KSV set type heavy quark to get the anomaly. So, but we introduce also right-handed neutrinos, and which get their Majorana masses also through the Pechek-Winn wave. Then you solve all the problems which I mentioned in the very beginning in the deduction, or nearly all the problems in one smash. So that you solve the strong CP problem, dark matter, inflation, neutrino masses, and mixing, and biogenesis via leptogenesis. So this is very, very nice. And this gives you a complete and consistent history of the universe from inflation to now. And it's very much testable in the next generation of Axion dark matter experiments and of CMB experiments. So this brings me now to my summary. So I find Pechek-Winn extensions of the standard model very attractive because the Axion solves the strong CP puzzle. The Axion is a dark matter candidate. This requires then a lower bound on FA or an upper bound on MA. The saxion Higgs is an inflaton candidate. And a Pechek-Winn standard model, Pechek-Winn extension of the standard model with saxion Higgs inflation is very predictive and thus experimentable, testable in the near future by CMB observations and Axion dark matter experiments. I think we should just stay tuned and let's see. So at least this theory can be falsified within my, hopefully, my lifetime. So thank you very much.
Okay. Thank you very much for the very comprehensive and interesting talk. I'm really excited to understand, to learn about all these things. So I will open the possibility to ask questions. So are there questions here? Okay, Luca, please go ahead, ask your question.
Very good. Hi. So
Hi.
First of all, thanks. It was really great.
Welcome.
So just a quick question on the last thing you said about inflation in Smash. But, you saw the parameter space NS versus R.
Yeah.
And your prediction, what runs on the curve is the number of E-fold.
Yeah.
That's the only parameter.
In principle, so we predict, so to say, we predict the number of E-folds, yeah.
Yeah, exactly, because you know the
and
potential.
you see, but you saw also, I mean, so in principle, so what you saw you saw this equal lines of psi sigma equal to 1, 10 to the minus 1, 10 to the minus 2, and so on, yeah.
Mm-hmm.
And this, so you see in a sense, so yeah. I mean, if they would now, so to say, if they would now measure this exactly here, this point, yeah.
Okay.
Then you could say, okay, this psi sigma must in our model. So if you interpret this in our model, psi sigma should be of the between say here 9 times 10 to the minus 1 and 0.9 or something like that. So from that you would learn something about square root of lambda sigma also, or lambda sigma, because of this correlation. So there is always a correlation between lambda sigma and psi sigma.
Okay.
So in principle, you measure, if this will be measured, then you learn even more about this theory.
Mm-hmm. Yeah. Thanks.
And what is also, I mean, there has been very long time ago, So-Young P, she has she was the first to say that the saxion could be the inflaton, yeah.
Yeah.
But without taking into account the non-minimal coupling. So this is of course excluded nowadays, yeah. I mean here above the highest line here, this corresponds essentially to psi equal to 0, yeah.
So that would be
would be the quartic inflation, but quartic inflation is ruled out already by the data, so to say.
Yeah. Okay. Thanks.
Yeah.
Great. Okay. There is a question by Carlos Yaguna.
Okay.
I will read it. Can you hear me? Hello? So I'll read the
We can hear
question.
you, Camilo.
Okay, so, what if a future experiment were to find a non-zero electric dipole moment? What would that imply for the axion?
This would imply, I mean, or even in a standard model, there is a contribution. There is a. We expect there to be a non-zero value of the. It's only the QCD part is set to 0 by the axion, but in principle. One has to see how big this electric dipole moment is then at the end. So, I mean, there's a very small value which will be induced by the CP violation in the standard model. There will be an induced electric dipole moment.
Okay. Well, I guess the question is, what would happen if it's bigger than what you would expect from the standard model prediction?
If it's bigger than from the standard model. I think, yeah. I mean, that would first. I would not see how this would be. This would be no problem for the axion, but yeah. How should we phrase that? So maybe I don't understand the question. So, but nevertheless, well, you could write me the question. I try to answer it.
Carlos, if you are here, if you're listening to me, can you reformulate the question? In the meantime, I can. Are there other questions here in the?
Yes, I have a question.
Okay, good.
So the action has this shift symmetry, but if I understand correctly, the saxion does not follow this symmetry, right? Because it's like the longitudinal component. Am I correct?
What do you mean by?
Because the action has the shift symmetry, right?
Axion has a shift symmetry, yeah.
But not the saxion.
The saxion has not a shift symmetry, yeah.
Okay.
Yeah.
That's one.
Yeah.
And I have another question. If you go back, I think, to your slide 29, when you show this plot of the next one, I think.
Yeah.
Exactly. 30. Just out of curiosity, what's this plot? What are you plotting there?
What is plot? This is something like the spatial average of the axion of the scalar field values. So one is, so to say, the as a function of time, yeah, and so and the time is in certain dimensionless units, so to say, and this Fi is in certain dimensionless units. What is illustrated here is in blue or in black. So black and blue are essentially at the beginning. It's the same line. So these are the oscillation of because this goes up to 1. These are the oscillations of the background inflaton field, so to say, yeah. So as soon as the field, so to say, you could see it like that. As soon as the field, so the inflation ends, so to say, when the field it rolls down this valley, and as soon as the field has a value of the order of M Planck, yeah, then it falls down into the standard model, into the direction of the standard model minimum, so to say, yeah. But at the beginning it doesn't feel everything which is going down here, but it starts to oscillate in around the 0 values, yeah. And so what you see here is the field evaluation when it oscillates around the vacuum, so to say. And then in these oscillations, because you have an expanding field in this oscillating, you can have parametric resonance production of the of the components of the fields which are parallel, of fluctuations of the field which are going parallel or perpendicular to this background field. So you are exciting, so to say, modes. You are exciting new spatially not constant modes in this background, yeah. And these are these fields which are starting here. And this is, so to say, you are now transferring, so to say, the energy from this homogeneous inflaton mode into the directions of the field space, into the other directions of the field space. And this, you see, already after a few oscillations of this field, after a few oscillations, this, so to say, you are starting to populate. Maybe you could look at, you are starting to you are starting to restore the Peccei-Quinn symmetry, because of course at the beginning the Peccei-Quinn symmetry is completely broken. You go in a certain radial direction of the Peccei-Quinn field, and this has a very large classical value. So effectively, you are not in the Peccei-Quinn symmetry phase, but symmetric phase. But when these other modes are excited, then effectively your theory is in the symmetric phase. So the symmetry is restored.
Okay, see, thanks.
Actually, I have a question. Well, I guess it's a very simple question on this slide. Why do you need to have a mixing with the Higgs?
This was because we considered in this paper, we considered both. We considered the case where lambda h sigma is larger than 0, then you don't have a mixing with the Higgs. Yeah, then you have only a valley along the rho direction. And then there we found in this case we don't have because we cannot get this nice effective production of standard model gauge bosons. We get a very suppressed, we get very low reheating temperature.
I see.
So the reheating temperature will then be only of the order of 10 to the 7 GeV or something like that. And this is then a problem with the axion dark radiation, because in this case the axions, because I mean in this reheating phase, I mean there are in principle you get then at the end you get a lot of relativistic axions, yeah. When this symmetry is broken, you have a lot of relativistic axions, and they should be also very quickly, if they are not thermalized, they will, so to say, we will get in nowadays so to say in the late universe, we will have too much relativistic particles, too much dark radiation. And so what we found is that for the typical values, for the typical parameters, we would get in pure saxion inflation, we would get delta nu n effective of the order of 1, which is excluded by CMB.
Okay, so I mean the bottom line is
by fine tuning of parameters, we have seen maybe it's possible. But we didn't investigate this longer because it seemed to us that the other possibilities and this other possibility arises just by flipping the sign of lambda h sigma from lower to larger than 0. We said, okay, this is certainly viable and everything works. But in pure saxion inflation, it seems to be problematic. But in principle, I think it would be a good thing to check this in more detail. But already now, so our paper was 100 pages, and therefore,
okay.
Therefore, we thought, okay, this is too much for us. Maybe somebody else can do it. But nobody did it, unfortunately.
Okay, there you go. So, are there more questions here?
Yeah, I have a question for Andrea. First of all, thank Andrea for this colloquium. It was very interesting, especially since I am not from I'm not expert in actions, but I was wondering, some kind of naive question is possible with the axion to fix this problem more or less that has the standard model with the metastability of the electron with vacuum?
I mean, here, so what we also did, I mean, this I didn't show here. We, of course, I mean, this is a Higgs portal model in a sense. Every Paget-Winn symmetry, every Paget-Winn extended standard model is a Higgs portal model. And now via this, so as is well known, you can fix the metastability problem by threshold effects if you have such a theory with a threshold effect. And we have explicitly shown also in this 100 pages long paper. So in this paper we have shown that you need something like that this model, and this we had to show. I mean, it's of course you have to show if you want to do this kind of saxion Higgs inflation, you should be sure that this theory can be used up to the Planck scale, yeah, or even a bit higher, yeah. You have to ensure that it's stable, so to say, in both in the Higgs direction as well as in the Paget-Winn direction, in the sigma direction. And so we did this, and we showed that through this mechanism, you get a condition on the threshold parameter, which is essentially lambda h sigma squared divided by lambda h or so, yeah. And this should be of the order of 10 to the minus 2. So to get vacuum stability and everything right. So it's true. I mean, you are solving in principle, you are solving also the vacuum stability problem, which I didn't want to add to this list. So you, with this extension of standard model, because we said this is part of the inflation price. So you should not have a vacuum stability problem, and therefore vacuum stability is part of inflation in a sense. But in our long paper we discussed this in quite detail.
Okay, thank you.
Yeah, you're welcome.
Okay.
Now I see again. I don't know why this. Do you also this infinity?
Yes.
Is it my fault? No.
Yeah.
Okay. Good.
Okay. Okay. So I see that there are no more questions. So then I would like to thank Andreas Ringwald again for this very nice colloquium.
You're welcome.
And yeah, then see you next time.
Okay.
Bye.
Goodbye. Ciao.